Okay, let's get started today's class. In the previous class, we briefly learned about the domain-specific architectures. So actually, in the first day of this course, I believe I explained about some semiconductor advances in semiconductor technology, and then the Moore's law is ending. So it means that it's very hard to make very good semiconductor devices. So everyone says that the Moore's law is ending, but the semiconductor industry is getting more important recently. Then I think it's obvious, okay? And then meaning that the Moore's law is ending is it cannot. It's very hard. So I cannot say you cannot, but it's very hard to make better processors or improve the processors. So recently, many researchers or companies, which means that processor industry also focus on domain-specific architectures. So which means that this domain-specific architecture has the specific hardware structure which can accelerate the performance of application in specific domains, such as the neural networks or parallel processing, like the GPU. So recently, so it's related to the some changes in the computing environment, and then also the changes in the computing industry. So which means that so recently everyone uses the smartphones, like mobile devices, and then actually these mobile devices are connected to cloud, and then so our data, so like the GPS data or some sensed data are collected to the cloud infrastructure, and then actually the cloud infrastructure runs lots of high performance server systems. And then actually these server systems require the specific domain of applications. So actually based on the Amdahl's law, which means that if the workload which can be improved by some ideas or architectural techniques, then we can apply these techniques. So recently the workload like the neural networks, also the graph analysis. So applications like these domains are being used more and more. So it means that the workload, some portion of this domain of applications are increasing. So if we apply some specific domain architecture which can accelerate the performance of these domains, then we can improve the performance of overall computing systems. That's why we are focusing on the domain-specific architectures. Also, then so if we use the better semiconductor technology, then we can build the more advanced processors. So which means it's faster, and then these processors may consume less energy. So which means it's energy efficient, but it's not fast. It's very hard. I cannot say it's not possible, but it's very hard. So that's why it's another reason we are focusing on the domain-specific architectures recently. And then actually today's class is the last regular class for this course. So in the next class, so in the next week, so we will take the final exam. So this is the last course. So in this course, I briefly cover the memory hierarchy of the computer system. So actually, I believe everyone already learned about the memory hierarchy, and then I believe most of you already knows about the memory hierarchy or memory systems. Okay, so why do we use memory hierarchy? It's very basic and fundamental knowledge in the computer architecture. So why do you use memory hierarchy? So because we don't have any ideal memories, so it's fine. And then what is ideal memory? What is an ideal memory? Fast, and then density is high, also the cost is low. So cost includes some manufacturing cost, also it includes the energy efficiency or power efficiency of the memory components. But we don't have any ideal memory components. So if the memory is fast, then the density is also low. So it means that so we need to use the very small size of memory, for fast memory. Also, this type of memory is very expensive, such as, so what is the most expensive memory? Usually the processor. SRAM. Okay. So SRAM is the most expensive memory component in the processor. So usually, so we can use the deep flip actually, but so sometimes we can use deep flip flops as the registers, but usually we use SRAM as the very internal, so on-chip memory, like the internal memory of the computer processors. So which means that the SRAM, the size of the SRAM is small, but the performance is high. So it is because SRAM is the one bit cell of the SRAM is composed of 6 transistors usually. So we can invest the more transistors for improve the SRAM, but usually, so typical SRAM has 6 transistors per one bit memory cell. So, and then, so as you can see, this is the static RAM. So, which means that the data stored in this SRAM memory itself is updated again and again, because in the bit cell of this SRAM, the data is connected, closely connected by 2 inverters. Okay, so which means that the stored data is updated again and again. So that's why the SRAM is fast and the SRAM is also expensive. But it includes 6 transistors per bit cell. And then usually, so we use SRAM cells for register file and then cache memories. So actually, until this, so these memories are included in the processor chip. So these memories are usually called the on-chip memory, because these are included in the single processor chip. And then as a main memory, so we use DRAM. Okay, so DRAM means the dynamic RAM. So the DRAM cell, actually one bit cell of the DRAM includes only 1 transistor plus capacitor. So compared to the SRAM, so actually the DRAM includes the less number of transistors, and then usually if you see some photo of the DRAM cell, you can find that the capacitor is fabricated like this. So we can build a very deep hole in the substrate, and we can make the capacitor of the DRAM. So actually the one bit cell of the DRAM is smaller than the SRAM. That's why the DRAM is less expensive than SRAM, but the performance is also low compared to the SRAM. Also, actually DRAM has many specific features such as so in the DRAM cell. So actually the electric charges are stored in this capacitor of the DRAM itself. So and then these charges are dissipated by time. So we need to refresh the stored data in the DRAM cell. So that's why DRAM requires the refresh period, and then these refresh periods degrade the performance of DRAM actually. Okay, and then after this main memory, then we can find the storage devices, and then we frequently use the hard disk drives or solid state drives as the storage devices. Okay, the storage device is very slow, and then but the density is very high. So it's another figure of the memory hierarchy. So you can find some typical access latency for each memory. Also, you can find some architecture of the memory hierarchy in typical complex system. So usually the commodity processors include until level 3 cache in a processor chip. And then usually the level 3 cache is the shared cache. And then actually, if we say a core, then a core includes until the level 2 cache. So that's why the level 2 cache is called the private cache. And then usually the level 3 caches are shared by multiple cores. So level 3 cache is the shared cache. So I frequently use this $ as cache. And we call the level 3 cache is the last cache in the cache hierarchy. So this level 3 cache is called the last level cache, LLC. Okay, so actually in the computer architecture field, we use many abbreviated terminologies. So we frequently use the LLC as the last level cache. And then actually this is a little bit old data. So actually recently, the access latency of the memory is like the tens of nanoseconds. Tens of nanoseconds is much faster than the 200 nanoseconds. But compared to these caches, the access latency is also higher than the internal memories like caches. And then if we consider the hard disk drive, then the access latency is like the millisecond unit. Okay. Then why do you use memory hierarchy? And then why this memory hierarchy is useful on a computing system? Because of characteristics of application. Actually, it's the characteristics of data used by normal applications. So actually, the memory hierarchy in computing the computer system explores the two types of locality, right? It's very, I believe everyone knows about the locality. And what is the locality? The temporal locality means that if our data is accessed, then this data will be re-referenced with high probability in the near future. So, which means that our data is accessed again and again and again. So the same data is accessed again and again and again. So this means the temporal locality. And what is the spatial locality? If our data is referenced and then in the near future, the neighbor data will be referenced with high probability. So this is the spatial locality. So actually memory hierarchy exploits the localities observed in normal applications. So that means if a certain applications do not exceed data localities, then we cannot benefit from memory hierarchy, right? So why mention this? Some applications, such as the graph applications that at the very large graph structure, do not exceed the strong data quality. Some data type exhibit the localities, but some data types do not exceed strong data locality. So which means that the conventional traditional memory hierarchy cannot exploit the data locality in such applications. Okay, so you need to also know why do we use memory hierarchy. If some applications do not exceed the strong data locality, then the conventional or traditional memory hierarchy cannot exploit the data locality in the application. Okay? Sometimes we can apply the specific data management or specific cache management or data management for such applications. Okay, so I already explained this. So memory hierarchy, so you can find the register. So register is located the closest register is the closest memory in the processor, which means that actually every instruction access registers to get operands, and then also the result of instructions are stored, so written back to the registers. Okay. And then you can find cache, the multi-level caches here, and then after that, you can find the main memory. But you need to focus on this one. So register is actually the number of registers is defined in instruction set architecture. So, and then actually these registers are called architectural registers. And then as we learned in the out of the processor, the number of physical registers can be different from the number of architectural registers. But actually, number of registers are defined in instruction set architectures, and then compiler needs to manage which registers are used in an application. The compiler decides which registers are used, and the high-level codes are compiled. Okay, so it's registers are managed by compiler. So which means that registers are managed by socket. So which means that so architectural register is different from the physical registers. And then because in the modern out of the processor, a processor includes the more physical registers. Okay, and then cache is usually managed by hardware. Right. So hardware decides which data is stored in cache or which data is deleted from cache. Okay. So this is the hardware area. So actually the instructions do not modify the data in cache usually. Okay, some instructions, some privileged instructions support the cache management, such as the Intel CL Flush, but most of the normal instructions do not manage data in cache. The data in cache are managed by hardware automatically. Okay, and then how about the DRAM and storage system? So these data are managed by operating system or kernel. Also, the data in the DRAM is managed by, it's handled by instructions like the load and store. Okay. So these are hardware part, and then these are software part. So the software manages the data in the main memory and the registers. The hardware manages the. And then when we mentioned some performance of the memory systems, we frequently use the average memory access time. So I believe so. You already learned about the average memory access time. So we can calculate the AMAC, this equation, the hit time plus this rate multiplied by this penalty. So and when we mention the performance of cache, we frequently mention this rate of cache. Okay, so what is the miss rate? And the cache is referenced, and then if the test data is found in cache, that is hit, and then if the test data is not found in cache, that is yes. So this rate is also critical for the performance of memory hierarchy on cache. suppose. Average memory access time is also determined by miss rate. But when we consider the performance of memory components, then we need to also focus on the heat time. So when the memory is accessed, the heat time is always included in the average memory access time. That's why the heat time is also critical for the performance of memory components. So the miss rate and the miss penalty is critical. Then sometimes we use the misses per instruction, the MPI, but we frequently use the MPI. Actually, we frequently use the MPKI because the misses per instructions maybe it's less than 1, because actually the caches are accessed by the load or store instructions, data cache. So every instruction will access the instruction cache, but this misses per instruction may be lower than 1. So we frequently use the MPKI. So this is per kilo instructions. So this is per 1,000 instructions. Okay. So actually, we can calculate the CPI at the baseline CPI, so which means that the cache memories are ideal, and then we can calculate the MPI multiplied by this penalty to calculate the effective CPI by normal caches, considering cache misses. And the miss penalty. So what is the miss penalty? It's the average delay cycles caused by cache misses. So actually, this miss penalty is determined by some access latency of low-level memory hierarchy. Like if we just consider the error cache, then it consider the access latency to the add to cache for misses. So actually, this miss penalty is determined by the access latency and the block size for block size of cache, also the access latency of the low-level cache. But if we use the out-of-order processor, it's very hard. It's very hard to calculate the miss penalty. So actually the effective miss penalty. It is a bit, and then also the processor architecture is getting more complex. So which means that we can apply the multi-threading also. And we use the out-of-order processor. Then it's not easy because when this occurs in cache, then just the load instruction is pending, but this is the out-of-order processor, so which means that other load instructions, also other instructions can be executed. And so if we use the speculative execution, these instructions can be executed speculatively. So which means that even though the load instruction is pending, so because of miss, then the following instructions can be executed in out-of-order process. That's why it's not easy. It's not easy. It's very difficult to calculate this penalty of the out-of-order processor. Okay? Because this miss penalty is default from this latency. So which means that even though it takes 100 cycles at cache for error misses, but these error misses can be hidden by some out-of-order executions or multi-threading, some other architectural techniques. So it's not easy to calculate the miss penalty. So usually we can measure the some we can measure the performance of cache using simulators. Okay. So and then so there are various cache mapping schemes, right? So and then I believe everyone knows. So we can use the direct mapped cache or set associated cache or fully associated cache. So direct mapped cache means that a cache set has only one block. Then set associated cache means that cache set can include multiple blocks. So actually, when the address is given to a cache, so this is the address that accesses the cache, then we can calculate the set index from the address that accesses cache. And then which means that this set index 1 is mapped to the one cache set. Okay? But direct mapped cache means that only this one cache set has only one block, and the set associated anyway set associated cache means that one cache block, one cache set includes n blocks. Okay? And then fully associated cache means that actually the cache has only one set, and then every block is included in this one set. So which means that data can be stored in every blocks in a cache. Okay? So the miss rate, if we just consider the miss rate of a fully associated cache is the lowest because the data can be stored in many blocks in a cache, but fully associated cache is so expensive. So if we just consider the cache, we can say that cache has the two components. Like the cache has the directory, and then also cache has the memory for storing data. So which means that the cache has the tag part, and then this tag part also includes the tag of the instruction, tag of the address, also any flag bits used by cache. So like we use many status bits such as the valid bit or dirty bit or reference bit or cache coherence bit. Okay, so these control bits are also included in this cache directory. And then also the data is stored in the cache. So then this data is stored in the data memory. So actually the cache has two components. It's a directory memory and then data memory. Okay. Also, which means that the cache access is the two pages. So we access the data memory with the index of the cache. So, right? So in the direct mapped cache, actually the cache has for one set, the cache has only one block. So which means that this block is read from the data memory, and then we need to check this data is the weakest data or not. So which means that we need to check the tag. Also, we need to check the variability or dirty bit and reference bits in the cache. So this information is read from this directory of the cache, and then we need to check the equality of the tag. Then in the address, and then the tag stored in the cache. So and then the result is determined. Right? Yes. So it is it's a direct mapped cache. So cache has the directory memory and the data memory. So just to compare the tag from this directory, and then for the set associated cache, then we just these tags are also a cache set, a single cache set includes the multiple blocks. So in this example, a single set includes the 3 blocks. So this is the 3-way set associated with cache. And then tags are also given to the cache directory, and then this tag is compared with the 3 tags in the set associated cache. And then, so actually, in the fully associated cache, then in the undergraduate course, we learned that the fully associated cache we require the number of comparators, which is equivalent to the number of cache blocks. But usually in the fully associated cache, we can use the lookup table, and then we can access this lookup table, then we can get the address of this data memory, then we can get data from the fully associated cache. Then replacement policy is also sometimes important. Okay, so for the set associated cache or fully associated cache, then blocks can. So in the fully associated cache, then we need the data can be stored in any blocks in the set associated cache, and a set is determined, and then this data can be stored in any blocks that are included in this target set. And then what is the replacement policy? When all blocks in a set are occupied, and also is the same to the fully associated cache, all blocks are occupied already, and then a new data is referenced to the cache, and then this event is missed, then we need to fetch new data block to the cache, right? So which means that target set or target cache are already occupied, which means that one of the blocks should be evicted. So one of the blocks need to be kicked out from cache. So then each block will be kicked out. So we can apply the random policy and the error loop, the recently used. Usually we can use this recently used policy. So also we can use the 5.4 or pseudo error. Okay. So sometimes this replacement policy can influence the performance of cache. Sometimes, but we frequently use the error loop policy because the error loop policy reflects the temporal quality. So, which means that if a data is accessed, then the same data will be accessed in the near future with high probability. But error loop does not represent the optimal policy. So what is the optimal policy? What is the optimal policy? The cache replacement policy. So actually, not to apply the optimal policy, then we need to know the lifetime of data actually. Okay, what does that mean? So in the optimal policy, so which means that even though this data is accessed, let us assume this data is A, but this data is recently accessed, but this data, the access for this data can be the final access. So this data will not be accessed again in the future. But because this data is accessed recently, so like there are some other data in C, D, when the new data is fetched in the cache, then this data D should be evicted from the cache. But the lifetime of this data ends at this point. Okay, so actually the error in this case, error is not an optimal replacement policy. So actually, the optimal replacement policy is possible if we know the future accesses to the cache, which means that actually if we know the lifetime of data in cache, then we can optimize the optimal policy, but it's not possible. It's not possible, but we can, so which means that we can estimate the some lifetime of data cache, but it's very expensive. It's very complicated. And then actually in the general purpose processor, it's not easy because so general purpose processor means that this processor needs to run applications in different domains. So which means that the data access patterns can be also various, so diverse. It's not easy to estimate the lifetime of data in the cache, but if we just focus on some specific domain of applications, then we can also estimate the lifetime of data in the cache. So in this case, we can apply some specific data replacement policy if we just estimate the lifetime of the cache. So actually, the optimal cache replacement policy varies by some characteristics of data access patterns of some data set used by applications. Okay, so we can actually for some specific domains, we can apply some specific replacement policies for cache memories. But usually we use the LRD, or LRD is also very expensive, so we can use the pseudo LRD. Okay. And then write policy, and then so there are two kinds of write policies. So write through and then write back. And then the write through means that for the cache hit case, so it's a write hit case. So write hit means that this is the store operation, and then by the store operation, the data in cache is updated. So this is the write hit case, and then for the write hit case, we can apply two different write policies. So one possible policy is write through, and then another possible policy is write back. Actually, most of commodity processors use write back policy because with the write through policy, then for the write hit case, the cache is updated, and then at the same time, the low-level cache or memories are also updated by this new data. This is the write through policy. But for this policy, and actually, if we just apply the very strict write through policy, then our instruction, the store instruction, needs to wait until this write operation completes in low-level cache or main memory. And then it will take a very long time, because why do we use cache? We want to reduce the access counts to the low-level cache, or access counts to the main memory. That is the main purpose of cache hierarchy. But if we use the write through cache and the write hit happens in cache, then this write hit will cause accesses to low-level cache or main memory. We want to avoid this case, so that's why we frequently use the write back policy. Okay, so write back policy means that for the write hit case, the data is updated only in cache, and then this updated block is reflected to low-level cache or main memory when this data is evicted from cache. Okay? And then what is the problem? So with the write back pilot, then this write operation is performed when this evicted block is dirty. The dirty means that the cache block is updated by write hit operation. So write operation is performed to the low level cache when this evicted block is dirty. Okay. And what is the problem? The problem is that it's coherence. So for the inclusion cache, then the same data can be found in level cache or level cache, here, like A and A. But when the write operation is hit in this level of cache for data A, then the data, this A is updated, like A1. This is the A0. So problem is that even though this inclusion cache, the level 2 and level 1 has the same data A, but the value of the data A are different for the write hit case. So this is A1 and A0. But if this cache is accessed by only this processor, then it's not a problem. So because this A can be only accessed by the CPU, and the CPU access this A, and this CPU will read the A1. It's not a problem, but if the cache is shared by multiple cores, or then actually the modern processors, most of modern commodity processors have actually multiple cores. So the problem is that if the main memory or the last level cache is shared by multiple cores. So it means that the different thread in the different cores can access the same data because when this data is not shared data. So it means that to the different cores can see the A0, even though this A is updated by this CP is core to the A1. But another core cannot see this update. So this is the coherence problem. So actually this problem is handled by cache coherence protocol, but in this course, we will not cover this cache coherence. So actually, as I will introduce some any following courses at this course, so that actually this cache coherence, so another issue is the memory consistency, and will be covered by other courses. Okay. But most of the commodity processor use the write back policy. And then 3 Cs of cache. So what are 3 Cs? So we can classify the cache misses. So actually 3 Cs define the causes of cache misses. Causes means why cache misses happen in a certain cache. 3 Cs explains the causes of cache misses. So the first miss is the compulsory, or it's called the code misses. So code misses happen on the first reference. It's the initial reference to a block. So for example, so usually in the initial state, the cache is empty. And in this case, and the reference is given to a cache, the cache does not have any data. So this is the miss actually, right? Also, another code miss is that the application firstly requests data A. So for the first time, it's the first access to the data A. But because this is the first access, this data A is not found in the cache. The cache does not fetch this data A, so this is the cold miss. Okay. So actually, then how can we reduce the cold miss rate? Can we improve? Can you reduce the cold miss rate? So cold miss is caused by first reference to a block, and how can we reduce the cold misses? So if the block size is large, then we can reduce the cold miss rate, right? So for example, when the A0 is adjusted, right? A0 is adjusted, then this is, if this axis is the first axis, then this is the cold miss. So, and then, but if the block size is large, then we can fetch the A0, A1, A2, or A. But many elements can be included in this cache block. And then actually when cache miss happens, then with the cache fetch the data block granularity. So which means that the entire block is fetched from the low level cache. So in this, and then after that, if the A1 is firstly referenced, but this A1 is found in cache because the block size is large. Okay, so if we increase the size of cache block, then we can reduce the cold miss rate. Okay, and then another miss is the capacity misses. So capacity means that the cache size is small, so which means so cache cannot include all data in the main memory. So, and then sometimes because of the limited size of cache, then cache miss can happen. Okay? This is the capacity miss. And the complete miss means that, and complete misses mean that, so if we use the fully associative cache, then we can, the miss rate of this fully associated cache is lower than either self-associated caches or direct map caches. The problem is that, the fully associative cache is very expensive. So usually we do not, the processors do not include fully associative cache. So because of this limited associativity in cache, then the miss rate can be increased. So this is called the conflict misses. Okay. Also, so I think actually if this is the associativity, x-axis is the associativity, and then this is the miss rate, hit rate. Then, so the hit rate is actually saturated by associativity. That's why we do not use the fully associative cache. Okay? So these are three things of cache. So, and then, okay. These are three things of cache. And so, and if we analyze these three things of the cache, then we can also figure out the causes of misses. Then we can also apply we can apply the different cache configurations to handle these different types of cache misses. And then recently we can consider another type of misses like called the coherence misses. So actually this miss also starts with C. So if we include this coherent misses, then these are called the forces of cache misses. Okay, so to find out, then how can we calculate the cold misses and capacity misses and conflict misses? Actually, the cold misses it's simple, because if we just assume that the cache size is infinite, and then if a certain data is firstly referenced, and this misses are cold misses. So cache size is, so if we assume that cache size are infinite, then we can calculate the cache misses. So these cache misses are cold misses, right? And then how about the capacity misses? So capacity misses, in order to calculate the capacity misses, we assume that our cache is the fully associated cache, and then this fully associated cache has the limited size. So, and then we can calculate the number of misses. So actually, number of misses for this cold misses. So cold misses. So this number of cold misses will be smaller than the number of capacity misses for this configuration, right? Because the cache size is limited. So we configure the cache with it's a fully associative cache, but the size is limited. Then this count will be larger than the cold miss number of cold misses, right? Because the size is limited. So how can we calculate the capacity misses? So while assuming this is the fully associative cache that has the limited size, and then we can collect the miss count for this cache, and then for this miss count minus cold misses is the capacity misses. Understand? We can calculate the capacity misses like this. So simulate fully associated cache with limited size, then deduct cold misses. This is the capacity misses. So when we calculate the cold misses, then we assume that this cache is the infinite cache. Then how can you calculate the complete miss? It's also same. Then we can configure cache like another cache associated, like the set associated cache, then count the miss numbers, then minus capacity misses minus cold misses. This is the complete misses. Okay. So that's how we can calculate the cold misses, capacity misses, or complete misses in a cache configuration. The problem is that we also need to consider the replacement policy. So which means that, so in this example, I assume that I just mentioned that when we calculate the capacity misses, I just mentioned how we assume that the cache is the fully associated cache. But the cache miss rate is also influenced by replacement policy. So which means that then when we measure the capacity misses, then we also mention which replacement policy is applied to this target fully associated cache. Okay. So this information is also given to when we calculate the cache misses. The multi-level cache. So we frequently use the multi-level cache, and then there are two policies like the inclusion cache and the exclusion cache. And then inclusion cache is simple. So which means that when the data is found in the this higher level cache, and the same data is found in the low level caches. Okay. So this is the inclusion cache. So also, which means that, so if data is found in the all levels of cache, and then if this data can be evicted from cache, like L2 data is evicted. So in this case, then we need to also evict the data in the level of cache. This is the inclusion policy. Okay, so which means that the definition of the inclusion policy is that if the data is found in a certain level of the higher level cache, and then the same data is found in the low level caches. Okay, so this is the inclusion policy. And then exclusion policy is that if the data is found in a certain level of cache, then this data only exists in this level of cache. This is the exclusion cache. So which means that when this reference is missed in the cache, like the error cache, then this error cache needs to fetch the data, which means that this data is fetched from the L2 cache. Okay, so here, and in this case, the data is removed from L2 because this is the exclusion cache. And then I explained that exclusion cache, if a certain data is found in the cache, and then this data exists only in this level of cache. Then if in the same way, if this data is evicted from cache, and then this data is also allocated in L2 cache, so low level of the cache. This is the exclusion cache. So actually, we can apply to some different policies to this inclusion or exclusion caches. So sometimes the policies are determined by this inclusion or exclusion caches. Also, like the cache parameters, you can consider some parameter configurations of the cache, like you can apply some larger cache blocks, or larger cache size, or larger cache blocks, or higher associated. So if we use the larger cache, then we can reduce the capacity misses, obviously, right? So we can reduce the capacity misses, but the problem is that the access latency can be increased because we use the larger memory components, and also the configuration is the cache hardware can be more complex. And if we use the large block, then we can exploit the spatial locality as I mentioned. So which means that if we apply the large block size, then we can reduce the cold miss rate. Okay? But the disadvantages in the large block size is the cache pollution. So what is the cache pollution? In the same size of the cache, if the block size is increased, then cache will include smaller number of blocks. But if because the block size is increased and the cache size is the same, then the number of blocks will be decreased. So, which means that this cache can include smaller number of blocks. Then actually the smaller number of blocks can handle a certain references, but these references are diverged, so which means that the access patterns are diverged in the cache. Then these caches are occupied by many divergent accesses to cache, but cache only include the smaller number of blocks. So in this case, if the divergent accesses, the divergent access patterns are exhibited in an application, and then this application references cache many times, then some blocks will be evicted, even though this block can be re-referenced again and again. This is called the cache pollution. Okay, so and then also this is called the cache crashing. Okay, So which means that because of the limited size of the cache, also the limited number of blocks in the cache, a certain block can be re-referenced again in the cache, but because of the limited number of blocks, this block is evicted from cache due to the many diverse accesses. So this is the cache tracing, but so this is also it's not good for the performance of caches. Okay. Also, when we use the large block, then the risk penalty is also increased. And then higher associativity. And then if we increase the associativity in cache, then we can reduce the conflict misses, right? But as I mentioned, actually the hit rate is saturated even though we increase the associativity in caches. So actually we can usually use the way or even the 16 way for the last level cache, or so we can usually use the 4-way cache in the error caches. Also, recently I found that Intel also used the 8-way cache for the error cache. Then I will explain about the lack of free caches, and then this cache is the non-blocking caches. So actually the cache is a two-ported device. So what does that mean? So cache is accessed by higher level cache or processor. The processor accesses the cache with some cache request, and then cache is also interacting with the low-level cache or main memory. Right? So if this is the L1, then the processor accesses the L1 cache with the cache request, and then also L1 cache interact with the L2, it's a low-level cache. So that's why the cache is a two-ported devices. And then the lack of free cache means that if this reference to the cache is missed, then the request is given to the L2. And then it will take time to fetch the data from the L2. So while doing this, miss is handled by cache, and then usually, but if we use the very old type of cache, then this cache cannot be accessed by processor. It's ridiculous, right? So when the reference is missed in the cache, and then the request, another request is given to the L2. And then while doing this, L1 is idle. L1 is doing nothing. But because this miss is not handled yet by L1 cache, then L1 cache cannot receive request from processor. So this is actually ridiculous, because while even though the L1 is idle, the L1 cannot receive any request from processor. So in order to avoid this case, we use the non-blocking cache, and then in order to implement a non-blocking cache, we require the MSHR. So MSHR is the miss status handling registers. So which means that when the reference is missed in the error cache, and then this request is registered in the MSHR, one of the MSHRs, and then while this request is given to the low-level cache, then this MSHR handles the missed reference. Okay, and then cache can receive any other request from processor while handling these previous misses. Okay, and then so some. You can say this is the memory component also. So this is called the MSHR, so this status handling registers, and then using this MSHR, we can implement the non-blocking caches. Also, no, actually, the out of the processors that we define non-blocking caches, right? Is it because even when the load instruction is missed in the cache, and then if the another load instructions cannot access cache, that means the out of processing is actually the performance benefit from out of processing is limited, right? Which means that the another load instruction needs to access the cache, is error cache. Okay, so this with the MSHL, then we can also implement the non-blocking caches and look at lockup free cache. But this number of MSHL, so which means that number of MSHRs means the number of pending misses. So which means that every access to cache is listed. And then if the MSHR, all of MSHRs are already occupied, then this cache cannot receive any request. Okay. So number of MSHR determines the number of pending misses. So like this. So actually the idea is very simple. So because the cache is supported devices, then if for the misses, missed response, then request can be also given to the low level cache. So while doing this, then cache can receive the other request. Okay. Which means that the miss penalty, then like some miss latency, maybe the miss latency can be overlapped of this cache. Okay. So this is the non-blocking cache, but you know, actually the most of all of the processors have non-blocking caches, right? So which means that the processors need to handle the multiple misses. And actually, if the processor implements the out of the processing, then we require the non-blocking caches, right? Also, if a processor handles multiple thread, so we also require non-blocking caches. Okay? So many requests can be many references can access cache. Cache needs a handler with multiple misses from many tasks. So let's take a break for 10 minutes. And then, so I will also explain some another topic, protecting virtual memory. Next. Okay, let's take a break 10 minutes. 이번 학기는 코로나 상황이 굉장히 심각한 상태에서 시작을 해서 처음에는 비대면으로 시작했고 그러면서 이제 대면 수업을 진행을 했는데 다음 학기는 아마 100% 대면 수업을 하지 않을까 생각하고요. 네, 일단 코로나가 이제 잦아드는 것 같고 이상한 병이 많이 생기면 넘기게 되지 않을까 생각을 하는데 거의 2년 동안 경험을 해보지 못한 이상한 전염병의 시대를 보낸 것 같긴 합니다. 근데 또 그러면은 거의 2년이라는 시간이 그렇게 짧은 기간은 아니기 때문에 사실 이제 노멀한 그 전에는 약간 이제 그런 비대면으로 이제 전환하는 적응을 했다라고 하면 이제는 노멀로 변하는 또 적응을 해야 될 시기에 살고 있는 것 같고요. 그래서 이제 다음 학기는 거의 이제 다 대면 수업을 하지 않을까 생각을 하고 있습니다. Okay, I resume the class. So another topic is the prefetching. So actually the most of commodity processor and prefetching engines, hardware prefetching engines, because if we apply the prefetching, then we can improve the performance. So what is that? So what is the prefetching? So for example, so if we frequently use this for iterative loop, and then when this iteration loop is performed, then we sequentially access the element of an array data. So usually this pattern, this access pattern is frequently found in the normal applications. So in this case, so this is the iteration loop, and then if we see the access patterns in the iteration loop, then we can find that this element of the array A is sequentially accessed like A0, A1, A2, and blah, blah, blah. Then, this iteration loop will perform some computation kernel that use the element of array A. So firstly, this array is fetched, requested with the load instruction, and then this array is fetched to the cache, and then the data is transferred to the register file, then data is calculated. So if we actually the hardware knows some sequence, the data access sequences for the certain array like A0, A1, A2, then the hardware can prefetch. The prefetch means that hardware estimate the next request. Then this request is fetched to some buffer or cache only. So this is the memory hierarchy pyramid. Then actually the cache and then actually the registers is managed by compiler, and then caches are managed by hardware. So it means that if hardware is prefetch some data to the cache or some buffers, it's not harmful. And then actually, if the prefetch is missed, so which means that the prefetch is not correct, but it's not harmful. It's just data is fetched and it's not used, but it's okay. Then if the prefetched data can be accessed in the future access, the future demand access, then it's good for the performance. Okay, so that's why the most of processor includes the prefetching engine. So actually, the Intel also actually commodity processors includes the prefetching engines. Okay, for every test level. Okay, so also this is the example of the instruction stream buffer in the instruction fetch engine. So actually, for the instructions are sequentially fetched with the PC plus 4. So which means that when the instruction is fetched, then before the real instruction is requested by a processor, the hardware architecture can fetch the future instructions from L2. So these instructions are fetched the I stream buffer, and then if these buffers instructions fetched to the I stream buffer is really demanded by a processor, so it's a real instruction, then this instruction is given to the instruction fetch queue. Also, the instruction is stored to the error cache, error instruction cache. Okay, so this is the prefetching engine for the error instruction cache. Also, we can apply the similar mechanism to the data caches, like error data cache or L2 caches also. So hardware prefetching engine also monitors some data access patterns for the certain stream. Then the prefetching engine estimates the prefetch address, then generate the request for prefetch data. So So you can find the prefetching engine between the L1 and L2, and prefetching engine between the L2 and main memory. So you can find the L3 here. So prefetching is the estimated request for future references. And then when we design a prefetching engine, then we need to consider the three performance factors. The first factor is the coverage, and then the second factor is the accuracy, and the third performance factor is the timeliness. So coverage means that, so this is the prefetching. Why is it so steep? So actually, this is the real demand fetch. So the prefetch is the estimated fetch for the future reference, and then demand fetch is the real request by some instructions or the processor of the instruction. So coverage means that this is the fraction of the demand fetches covered by prefetch. So for example, this is the amount of demand fetches, and then with the prefetching engine, then we can cover some part of the demand fetches. So this means the coverage. If the coverage is high, then which means that we can get the large amount of demanded references using the prefetching engine. So prefetch covers the large amount of data. Then which, if the coverage is high, then we can increase the performance of prefetching. And then accuracy. This is also important because prefetch is the estimate with the prefetching, and we need to estimate the addresses of future accesses. So this is the estimated addresses. So which means that this estimated addresses can be correct or not. So why this accuracy is important? If this estimation is incorrect, then actually this prefetching engine will test the unnecessary references. And then these unnecessary references will consume the hardware resources in memory hierarchy. Okay, so actually, some processors, the bandwidth is very critical for the performance. But if the prefetching engine generates many inaccurate prefetching requests, then these inaccurate prefetching requests will consume the resources in the memory hierarchy. So which means the bandwidth, the actual bandwidth is reduced, occupied by inaccurate prefetches. So accuracy is also important. The timeliness. So why timeliness is important? So for example, so this is the latency of the real demand fetch. Okay. Then what is the purpose of the prefetch? The main purpose of the prefetch is to reduce the long latency for data fetch. So which means that if the prefetch request is generated at this point, so this is the latency of the demand fetch, and then if the prefetch request is given at this point, then this can be the latency of the prefetch. So because the prefetch is given just before many cycles of the demand fetch, then we can say this amount of cycles for demand fetch. But let us assume that the prefetch is given at this point. Then we can just say this amount of cycles. So which means that with the prefetching, then we can just reduce this small amount of cycles for real demand fetch. So timeliness is also critical factor for the performance of prefetching engine. Okay. So we need to consider the coverage, accuracy, and timeliness of the prefetcher. And then, so also the prefetch can be generated by instructions, so compilers. So some instructors and architecture define the prefetch instruction, and then compilers can include those prefetch instructions in the iteration group. So this is an example. So you can find the prefetch instruction here, 3 minus 24. So this, because this prefetch instruction, this data is not stored in the register file, but this data is just fetched and then stored in the cache. But you know, you can find the some offset of this prefetch test. So with this instruction, the compiler can insert this prefetch instruction in this loop, and then compiler can prefetch some data for the future loop iterations. Okay, and then so with this, also we can so these iteration loops are analyzed by compilers. So and then we can also figure out some real data references or the real data request from an application. So that is the advantage of the compiler controlled prefetching. But this disadvantage is that the instructions are occupied. So which means that this prefetch instruction needs to be decoded by hardware, or so it's decoded by hardware. So it means that this is the instruction avoided by a prefetch software prefetch instruction. Also, actually the compiler does not know the real execution environment in a CPU. So this is also important. So it means that as actually when the data is prefetched to the cache, then not to use this data in cache, then this data should be kept in the cache, right? So, and then if this data is fetched to the cache too early, and then it means that because of cache stressing, this prefetched data can be evicted from cache. Okay? So which means that the timing of the prefetch is also very important. So actually the compiler does not know the real situation of the computer hardware, so which means that this prefetched instructions to be performed, and then the data must be kept in the cache. But compilers cannot control this. So we need to consider some timing of the prefetch. Okay. So actually there are many mentioned some level of cache. There are two different types of level of cache. So for instance, architecture and then Harvard architecture. And then actually the most of processors is the Harvard architecture, because in the Harvard architecture we split the data cache and then instruction cache, the level of cache. Okay. Okay, so I'm going to skip here, and then virtual memory. So, I believe so the virtual memory is briefly covered in the undergraduate computer architecture course. So I believe everyone knows about already knows about the virtual memory. Okay, so virtual memory means that it's another abstraction of provided to the software. So why do you use virtual memory? Actually, the original purpose of the virtual memory is to use main memory like cache. Okay, so in the old computer systems, actually all the computer systems have a very small size the main memory, like the 640 kilobyte, 640 kilobyte. So this the size is very small. So And also the memory was very expensive. So we won't use this memory like the cache, because the memory is the very precious resources in the computer system. But relatively, the disk size is larger than this main memory. Also, this place was cheaper than the main memory. So we can use this large space of the disk as the large space of memory. So actually, the virtual memory is invented to use the main memory like cache. So which means that actually this is the size of the physical memory, but to the software, the processor gives the illusion to the software that, oh, we can use this large memory. But this is a fake memory. So this is not real. So this is the size of the real physical memory, but we won't provide the large space of the virtual memory because it's fake. So some data can be stored in this physical memory. So the hardware just supports the virtual memory space, and then based on the virtual memory space address, then this address can be mapped to the data in the physical memory. So then, which means that we can access this data very quickly, but some part of the address is mapped to the space in the hard disk drive. So in this case, so this data will, when we a software access this data, then it will take a long time. But we can manage this virtual memory space like cache. So which means that the frequently used data is stored in the physical memory, and then some cold data, so infrequently accessed data is stored in this data disk. But to the software, then the processor can provide a very large virtual memory. So it means that actually this is the main memory space shown to the software. So software does not know this data is stored in the main physical memory, or this data is stored in the hard disk drive. Okay. Actually, the processor just provide one large virtual memory space. Okay. But in reality, some data in this virtual memory space can be found in the physical memory, and then or some data in this virtual memory space can be found in the hard disk drive. Okay. So in order to support this, then the software accesses this large virtual memory space with the virtual address, but in order to access the real data, this virtual address will be translated into physical address. So which means that even though the software accesses the data in the virtual memory space, which means that the data in the fantasy world, but when you access the real data, then we need to go to the real world, then you need to access the data with the physical address. So actually virtual memory, in order to support the virtual memory, the hardware provides the translation between virtual address to the physical address. So that is the concept of virtual memory. But recently, the computer systems have a very large sized main memory, but we still use the virtual memory, because if we use the virtual memory concept, then it is very convenient to manage the memory spaces, the physical memory spaces. Also, if we just provide the virtual memory concept, the software engineers do not need to concern about some data management or some memory management in the real computer systems. So what does that mean? Actually, it's very hard to manage the data. So which means actually in a real computer hardware, many processes are running. So if you check the running processes in the Windows, or you can check the running processes in Linux operating system with a top command. But if you check the running processes on your computer system, then you can find that many. So lots of processes are running. But which means that these lots of running processes need to share the main memory space. Right. So in the many applications, like many processes, need to access main memory, share the main memory. So the processor is supposed to run large physical main memory spaces. So which means that we need to assign this physical main memory to many running processes. Software cannot manage. Hardware and operating system, because operating system manages the hardware resources in the computer systems. So operating system and the hardware can manage the resources in this real computer system. Okay, so to the software has the illusions. So that which means the software runs on fantasy world, because the operating system and the hardware just provide a very large virtual memory space and then unlimited number of cores. Okay, so it means the unlimited number of processors to the software. So when the software engineer write the higher level code, they do not consider about the size of the physical memory. You know, the size of the physical memory is very critical for the performance. So we already know. But when we write a code, we do not consider about the size of the physical memory. But it's very critical for the performance. So everyone needs to consider some limited size of the physical memory. But we can actually, theoretically, the software can access the very large memory, the virtual memory, because the most of the processor supports the 48 bits of the memory address. So actually, I believe everyone knows that when the load instruction is accessed, then this address is the virtual address. Okay, and then so with these 48 bits of the address, then we can access the large virtual memory space, like the 256 terabyte. Okay, it's very large. But actually, our hardware has the very small physical memory. So some data is mapped to the data in the real physical memory, but data cannot be mapped to the physical memory space. But it's fine. Software does not consider, software engineers do not consider about the limited size of the main memory. So they just write the code. Then these hardware resources like the memory spaces or the number of cores are managed by operating systems and then computer hardware. Okay, so the software is launched, which means the application is executed and the virtual memory space is assigned to this software. And then to the software side, then it is shown that the software access the same address like 0001, 0x0002, blah blah blah. But these default addresses are virtual addresses, and then these addresses are mapped to some different location of the physical memory. Okay, so this is very important and very critical for the software running environment, because if with this virtual address concept, we can separate the physical memory space assigned to the software. Right. The software 1, even though this is the software 1, this is software 2, then the software accesses the same address like 0x010, 0x0010. So this is the different data. In this case, then we can access this address to the some physical address 1, this address to the physical address 2. So we can separate the assigned space in the physical memory with the virtual memory concept. So we can protect the data from one software to the other softwares. Okay. So we can this physical memory can be shared by multiple running processes. So I believe everyone knows the concept of the virtual memory. So, and then usually we use the paged virtual memory as segmented type virtual memory, because most of the processors support the page type virtual memory because it's invisible to the programmers. Okay, then but it's efficient for the disk data tracking. So just consider the page type virtual memory, and then so I believe everyone knows about the virtual memory concept. But in order to implement the virtual memory, then this virtual page number should be translated into the physical page number (PPN). But we configure the size of the page. So this is the page type. So we frequently use the fixed page size like 4 kilobyte. So which means that this 4 kilobyte chunk is translated of the virtual memory block is translated into the physical page block. And then this block is called the page. So then usually we use the 4 kilobyte of the page size, which means that the row, the LSB 12 bits of this address is directly copied to the row part of the 12 bits of the physical address. Okay, because this is the page offset. But when you consider the virtual address, so actually virtual memory space is assigned to each running process. So which means that this can be observed, virtual address mapping. So you can find that. So this is the virtual memory space for process 1, and this is the virtual memory space for process 2. And you can find that this virtual address is different. So VA1 and VA2 are different. But as you can see by the virtual address to the physical address translation, VA1 is mapped to the PA1, also VA2 is mapped to the PA1. The same address is pointed by different virtual addresses. And then this is called synonyms. Okay, so VA1 is not equal to VA2, but VA1 is not translated to PA1. VA2 is also translated to the same PA1. This is also possible because some data can be shared by different processes, also some libraries can be shared by different processes. Okay. So another observation is that virtual address is the same, but these virtual addresses are mapped to the different physical addresses. But it's obvious, right? So these are different processes, which means that it's a different application. So independent processes. So even though the virtual address is the same, then this data is different. So it can point to different physical addresses. But then this is called the homonyms, but it's Actually, this is the obvious to the virtual memory concept. Actually, the virtual memory signaling is the so we need consider the synonyms. So which means that even the virtual address is different, but the physical address is the same. So which means that the same data is pointed by different virtual addresses. So called the synonyms. So this is the page virtual, and then so actually for this virtual address to the physical address translation, we use the page table, and everyone knows that the page tables are managed by operating systems. So which means that when an application is executed, so it can execute a certain application by some command, like click some icons in the Windows operating system. We can also run applications by using some command, okay, in Linux. So when an application is executed, then the virtual memory space is assigned to this application. So which means that the page table, the operating system builds a page table for this launch application, and then this page table is assigned to the running process. Okay. So the page table has some virtual page number to physical page number translation information. Also, it has some additional control bits like the permission bits, and then some protection bits, and then also it has the dirty bit because we use the main memories like the caches. So this physical page entry includes the additional control bits. Okay, so that's how the virtual page number is translated by page table using page table like here. So actually the location of the page table is pointed by page table base address. Okay? So the page table is built by operating system, and then this page table is stored in the main memory, the physical memory, right? So in order to access the page table, so it's a virtual page number is given. Then we need to translate this virtual page number to the physical page number. But which means that we need to access the page table in main memory. And then the location, the pointer of the first address of the page table is pointed by page table base address. And this address is stored in the registers in a processor. So in the virtual page number is just so we use this virtual page number as the index or some offset to this page table, and then we need to add this page table base address to the virtual page number, and we can access the entry an entry in the page table. And this entry includes the PPN, the physical page number, and then control base here. Okay. Here, and then you can get the physical page number here, and then you can get additional control bits here. You check the rights or permissions of the virtual page. And then these are page offset. So page offsets are just copied. So you need to access data with this real address, this physical address, right? Because data are real in the computer system. But what's the problem? So if we use the single level page table, then the size matters. So think like this. So if we assume that the virtual address, the size of a virtual address is the 48 bit, and then and size of the single page is the 4 kilobyte, which means that the size of the virtual page number is the 36 bit. So because the virtual page number has 36 bits, then this page table will have 2 to 36 entries. Okay? It's very large. But what is 2 to 36? It's the 64 giga entries. Okay? It's ridiculous. So we cannot manage, actually this virtual page table is assigned to each running speed, running process. So, and then, we can find a bunch of processes, bunch of running processes on our computer system. So, and then, let us assume that this page table is assigned to each process. It's ridiculous. It cannot, we can generate, the operating system cannot generate this large size page table. So we use the hierarchical page table. So with this hierarchical page table, then we split the virtual page number to the, in this example, the three parts. Then the first with this V1 just refers the level of page table. Okay, and then with this level of page table, this we can get the references to the leveled page table. Okay, so some base address for the leveled page table, and then this base address is added to the by some other part of the BPM, the B2, and then we can also access the entry of the leveled page table. But the output of this leveled page table is the base address for leveled page table. Okay, then we can just access the leveled entry of the leveled page table using this base address and the offset from B3. And we can get the legal page number. So using this multi-level page tables, then we can reduce the size of the page table. So I explain about the I will show the user this slide. Okay. So in this example, the virtual address has the 42 bits, and then the physical address is the 32 bits. So which means that is the size of the physical memory is the 4 gigabyte. So reasonable, right? And then page size is the 4 kilobyte. So which means that the page offset is the 12 bits. If we just use the one level page table, and then let us assume that the size of the one page table entry is 4 byte. So in this example, so as you can see, the operating system assigns the kernel part, and then this is the code part, and then this is the static data, and this is the dynamic data. Okay, so the static data is assigned to this virtual memory space. Then the code is assigned the instructions. So the dynamic data is assigned to the 2 megabyte. Okay, so the step. So if we manage this virtual memory space with the one level page table, and then if we assume that the size of a single page entry is the 4 byte, this one level page table will have 2 to 3 entries. The size of the page table is the 4 gigabyte. That's right. And then you all know that the size of the physical memory is 4 gigabyte. So one page table occupies the entire space of physical memory. It's ridiculous. It's not possible. Okay. But if we use the 2-level page tables, and then this BPN is split into the 50 bit and then another 15 bit, then the size of the level has the 2 to 15 entries. Okay, the size is the 4 kilobyte. So it's a 128 kilobyte. And then if we use the level 2, this level page table is entries to the only valid area of the virtual memory space. So kernel region is not translated. Okay, so we don't need to have some translation for this kernel region. So actually, for this process, the operating system provides the page table for this code area, and then dynamic data area, and then static data area. Okay, that's why the level 2 for the level 2 page table requires just two page tables, because this one you can calculate the size of the level 2 object. So actually, the one entry is mapped for the level 1. The one entry is mapped to the 120 megabyte. Okay, so which means that one level 2 page table occupies the 128 megabyte from this code area. Also, another 128 megabyte can be covered by another level 2 page table. So 128 megabyte, right? So that's why we require only 2 level 2 page tables. And then because this is the 15-bit, so the level 2 page table size is the 128 kilobyte. It's the same. So the level 1 page occupies the 128 kilobyte, and the level 2 page table occupies 128 kilobyte, and then we require 2 level 2 page tables. So it's 256 kilobyte. And then it's about the 384 kilobyte. So it's reasonable. Okay. And then if we use the 3 level page tables, then it's a 10 bits. Then so it's the level each page table occupies the 4 kilobyte. Then and then actually for the level 3 page table, we require the 3 level 3 page tables. So the entire size of this page required page tables for this application is the 24 kilobyte. So compared to this 4 gigabyte, it's a 24 gigabyte is reasonable. Okay, right? It's actually very small compared to the 4 gigabyte of page table. So which means that actually we need to use the hierarchical page table to reduce the size of page table. Okay. So what's the problem? I said the page table is stored in the main memory. So in order to get the physical page number, so with the hierarchical page table, we need to access main memory 3 times. So when the load instruction is executed, then load instruction execute the address, execute the data with the address, but this address is the virtual address, right? So it's a virtual address, and then this virtual address needs to be translated to the physical address to access real data in memory. So, in order to access the data, then this virtual address needs to be translated into the physical address, but for this translation, we require 3 memory accesses. So why do we use cache? Actually, not access the cache, we use cache to reduce the memory accesses. But because we are using virtual memory concept, for this translation, we require 3 memory accesses for each translation. So it will degrade the performance dramatically, right? So that's why we use TLD that everyone knows. So TLD is the cache of the page table. So actually, people, so this VPN to PPN translation information is cached the TLB. Okay, so you know the page size is just 4 kilobytes. It's very large compared to the data accessed by application. Also, because of spatial locality, most of the data accessed by an application, sometimes window can be included in the one page, right? Because of spatial locality. So, which means that for the first access, that we can fetch this full VPN to PPN information to the TLB, right? And then after that, using this cached translation information, then we can quickly translate the virtual address to the physical address. Okay, that is the purpose of TLB. And then actually, usually there are two TLBs for the level of cache because the caches are separated. So we actually, this is the some write operation of the TLB. So which means that when the processor accesses the cache with the virtual address, this virtual address needs to be translated into the physical address by TLB. And then if the TLB is missed, then using the page worker, then we need to access the page table. But if this translation information is found in TLB, then we can get the physical address quickly, and with this physical address, we can access the level cache. Okay. So this is a typical memory hierarchy. So usually the size of the level of cache is small. So using this page offset, so actually, even though the virtual address is translated the physical address, this page offset part is maintained, it's kept the same, right? So, and then if we just split the address to some cache index or cache tag, so you can find the block offset part in the row part of the address, and then you can find the index part. Also, we can find the tag part in the address. So, if this index part occupies some lower bits of some bits lower than the page offset part, like the bit number 11 to 0, and then if this index is included in this page offset, then we can access this level of cache with this page offset. Right. So this is the index part. Index part is included in the page offset part. So you can access cache data. So data memory, so we can get tag from cache. And then using the TLB, the virtual page number is translated into physical page address, then we can get a real tag. Okay, and then this tag is compared with the tag in the cache. Okay, because the index part is included in the page offset. Okay. And then usually the level to cache size is larger than the level of cache, and then which means that the level to cache, the index of the level to cache actually is larger than the page offset part, right? So which means that this is the index of the level to cache, and this is the part of the level to cache. But it's not a problem because we already get the physical address from TLB, so we can access the level to cache with this physical address. Okay, the problem is only for the level of cache. But the problem is that if we access the level on cache using this physical address, translates the physical address, then we need to wait until this physical PPM is. We need to wait until we get PPM from TLB. So this will increase the heat time of cache. Okay? Then that can be the problem. Also, if we use the larger cache, which means that if we increase the size of the level on cache, then index part of the level on cache can occupy over page offset part like here. Okay. So in this case, there can be coherence problem. What does that mean? So in a typical memory hierarchy, then we first access the cache with this index part. But index part in this example, the index part is found within the page offset. But if this is increased, then the index part also includes the part of virtual page number. This is the part of virtual address. So if we just use the page offset bits, then this page offset bits are same to the page offset of the physical address, which means that we can access the cache with the physical address. But problem is that if we use the larger cache, and then the index part is larger than this page offset part, then part of virtual page number is included in the index of this cache. And problem is that for the synonym, the virtual address can be mapped to the same physical address. So in this case, the data is the same. Nearly, this data is the same. This same data is accessed by different virtual addresses. So if this part of virtual page number is included, then the cache index can be different because part of the virtual address is included. Right. But for the synonym case, index is different, but it can point the same data. Which means in a cache, this is the data that has the same address, same physical address, but this data is stored in the different blocks in cache. Okay, that's the problem. So what's the problem? So this data can be also updated by another process, but this process 2 is the old data because the data is stored in the different blocks in a cache. So it's called the virtually indexed cache. Then we need to solve this. This is the aliasing problem. So which means that in our cache, the different virtual address are used by different processes, and then the virtual page number is included in the index part of the cache. Okay, so this is called the aliasing problem, and then not just solve this aliasing, and we can apply some techniques. We can check actually every access is by this virtual address to the physical address. So in this case, so also another problem is the increase the heat time by TLB accesses. So in order to avoid this case, then we can also locate the TLB after the error cache. So which means that the error cache is accessed by virtual address only. Okay. So in this case also, there can be the same problem. There can be same aliasing problem because the cache is accessed by virtual address. Okay. So we need to also handle this issue cache. So, okay. So this is the end of the virtual memory. And then actually, I explain about the multi-level page table, some advanced concept. Then I include the virtual addressed cache. Okay. Okay. I close the. Oh, there is the. Sometimes the OneDrive is not updated. Okay, so I closed the. So this is the last topic covered by this course. And then, so as I introduced in the syllabus, I covered some advanced topics in computer architecture field. I don't know why the OneDrive is not updated by some new slides. So I will share the slide on the Piazza Blackboard. So in this course, we learned about the advanced topics in the computer architecture. So I believe everyone already learned about some basic topics in computer architecture field, the undergraduate computer architecture course. But in this course, it covers some advanced topics, such as the technology trend, and then so the out of the process of architecture, so predictors, speculation, and then VLIW, GPU, PSA, so some advanced topics in memory systems. Okay, so and then in the next class, so it's the last class of this course, so we will take the final exam. And then, as I mentioned, the final exam is the open book exam. So you can refer on any slides, you can refer any physical papers. You can print out papers and you can see also any materials. Okay? Any physical material, not virtual material. So this means that you cannot access electric devices during the exam, except very simple calculators. And then, actually, I think the estimated exam time is 2 hours, but maybe it can be extended. And then, so actually, after this course, you can also explore some advanced topics in computer architecture. So, and actually, in this course, I introduced some more advanced architecture, the modern processors. So I also introduced some advanced topics like some specific architectures such as the VLIW, GPU, PSA. But these are also need to be explored further in some different courses. So also in the memory system, I briefly explain about some advanced topics in memory systems, but in the multi-core architecture, we need to also consider some very difficult concepts such as the coherencies or consistencies, also like these protections like this. So actually, in the next semester, I will provide the GPU architecture course. So it means that we will deeply dive into the GPU architecture. So we will learn about some simple CUDA programming, how the GPU software works in the GPU hardware, the GPU architecture. So we will also cover some more advanced, more advanced architectural issues in the GPU architecture. And then also the next semester, I believe that another course like the parallel process architecture will be provided. And then in the parallel process architecture, then you will learn about the issues in the memory systems and chip multiprocess architecture, like the multi-core architecture. So like cache coherence and then cache memory consistency, these are also very important topics in the multi-core architecture, chip multiprocessors also. These are also very important topics in modern memory systems. Okay. Also, our graduate school provides some other advanced courses such as the advanced process architecture or domain-specific. Also, I will provide a new course called the domain-specific architecture in the next year. Like also memory systems or storage systems. So if you are interested, then you can take the more advanced course. Okay, so in this course, I introduced some advanced topics in the computer architecture field, but this is also the basic. So it's the fundamental, it's a start point of the computer architecture research, actually. Okay, so it's an advanced topic, but the start point of this computer architecture research. So if you are interested, then I recommend you take some advanced level of course, as I introduced in now, like the parallel process architecture, and GPU, DSA, storage or memory systems, advanced process architecture, something like that. Okay. Okay. So I will close the course. Then we can meet in the next class. So we can meet the final exam the next week. Okay. So any questions? Okay, thank you for your attention. Thank you for your interest in this course. And good luck for the final exam.